Dear students, welcome back to the lecture series on solid state. In the previous class, we have discussed about packing of uniform spheres or packing of atoms in different types of cubic lattices, namely face-centered, body-centered and simple cubic lattices. And we have seen that the simple cubic, body-centered and face-centered cubic lattices varies in their packing efficiency. So, today we will discuss more about packing efficiency. We will be seeing how packing efficiency varies in face-centered, body-centered and simple cubic structures. We will also be discussing a few problems based on tetrahedral or octahedral voids and thereby finding the formula of the compound. In the last class, we have seen that the packing of spheres in simple cubic, body-centered and face-centered arrangement gives rise to a packing efficiency of 52.4% in simple cubic lattice, 68% in body-centered cubic structure and 74% in face-centered cubic structure. So, let us see how to theoretically calculate such packing efficiency. So, before moving on to calculation of packing efficiency, let us see about packing fraction. So, what is packing fraction? It is the fraction of the total space filled by the particles in a certain packing, or it can also be represented as the volume occupied by the spheres in the unit cell divided by total volume of the unit cell. So, as the name suggests, packing fraction is a fraction, so it is always less than 1. For example, the packing fraction of hexagonal close packing as well as CCP is 0.74. Okay. So, in terms of packing fraction also, we can represent the volume occupied by the spheres in various cubic lattices. So, packing fraction is nothing but the fraction of the total space filled by the particles in a certain packing, represented by volume occupied by the spheres in the unit cell divided by total volume of the unit cell, and it will always be less than 1. So, what is packing efficiency? Usually, we represent the volume of the spheres occupied in a cubic unit cell in terms of packing efficiency. So, the percentage of the total space filled by the particles in a certain packing is called packing efficiency. And we can represent packing efficiency in this form, that is volume occupied by the spheres in the unit cell divided by total volume of the unit cell into 100. So, it is usually represented in the form of percentage, that is why it is multiplied by 100. So, packing efficiency is the percentage of the total space filled by the particles in a certain packing, and it is given by volume occupied by the spheres in the unit cell divided by total volume of the unit cell into 100. So, now let us see how to calculate packing efficiency in various cubic lattices. First, let us see how to calculate the packing efficiency in a cubic close packing or face-centered cubic arrangement. So, on the screen, you can see a figure showing a face-centered cubic arrangement. For clarity purposes, only the spheres on one face is shown here, and we have marked the face as A, B, C and D. So, let the unit cell edge length. So, unit cell edge length, it can be either AB or it can be either BC. So, AB or BC. So, let it be A. We also have marked a face diagonal. So, this is the AC. AC is the face diagonal, and let face diagonal be B. Okay. Now, on the figure, consider the triangle ABC. So, this is the triangle ABC. We know that from geometrical considerations, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So, when we consider the triangle ABC, we know that the square of the hypotenuse, that is AC, is the hypotenuse. So, the square of the hypotenuse AC square will be equal to the square of the other two sides. So, what are the other two sides? We have AB and BC. So, AC square will be equal to AB square plus BC square. AC is the face diagonal and we have denoted it as B, the length is B. So, we have B square is equal to A square plus A square, where A is the edge length, or we can write B square equals 2A square. So, what will be B? B equals root 2A. So, we have obtained a value for the face diagonal, that is B equals root 2 into A. Now, let R be the radius of the sphere. Okay. So, here you can see that the face diagonal AC equal to B, and that is equal to 4R. So, how 4R? You can see that on this face there are 3 spheres touching each other. The radius of one sphere is R. If we look at the sphere in the middle one, it is touching the 2 other spheres. Okay. So, here it is R. At the middle sphere it is 2R, and in this sphere this is also R. Okay. So, R plus 2R plus R, so that give rise to 4R. So, we can write 4R is equal to root 2A, since we got B equals root 2A. So, 4R is equal to root 2A. So, what will be A from this? A equal to 4R by root 2. So, we can simplify this by multiplying and dividing by root 2. So, root 2 by root 2. So, that will be equal to 4 root 2 R by 2. So, that will give rise to A equals 2 root 2 R. Okay. So, we obtained the edge length in an FCC lattice as A equals to root 2 R. We know that in a CCP or FCC structure, each unit cell has effectively 4 spheres, or we may say there will be 4 atoms per unit cell. So, what will be the volume of these 4 spheres? So, the volume of the 4 spheres will be equal to 4 into 4 by 3 pi r cube. Now, what is 4 by 3 pi r cube? 4 by 3 pi r cube is nothing but the volume of one sphere. Volume of one sphere is 4 by 3 pi r cube. We have 4 spheres per unit cell in a FCC lattice. So, volume of 4 spheres will be equal to 4 into 4 by 3 pi r cube, which is equal to 16 by 3 pi r cube. So, we got the edge length A equals 2 root 2 r. The volume of the 4 spheres 16 by 3 pi r cube. Now let's calculate the total volume of the cube. Total volume of the cube is the cube of edge length, that is A cube. So that is equal to 2 root 2 r the whole cube. That will be 16 root 2 r cube. So 2 root 2 r the whole cube means 2 cube is 8 into, we have root 2 cube. So root 2 into root 2 into root 2. So 2 root 2. So 2 root 2 r cube. So that will be equal to 8 into 2, 16. So 16 root 2 r cube. So we got the total volume of the cube A cube is equal to 16 root 2 r cube. So now let's calculate the packing efficiency. We have seen that packing efficiency is the volume occupied by the spheres in the unit cell divided by total volume of the unit cell into 100. So here there will be 4 spheres per unit cell. So the packing efficiency can be represented as volume occupied by 4 spheres in the unit cell divided by total volume of the unit cell into 100. Volume occupied by the 4 spheres is 16 by 3 pi r cube and total volume of the unit cell is 16 root 2 r cube. So into 100, so that will give rise to 74%. So we can say that the packing efficiency in a cubic close packing or face centered cubic arrangement is 74%. In the previous class, we have seen that hexagonal close packing is equally efficient as CCP or FCC. So we can say that the packing efficiency of hexagonal close packing is also 74%. And the hexagonal close packing and cubic close packing are considered to be the most efficient ways of packing, giving rise to a packing efficiency of 74%. Now let's see how to calculate the packing efficiency in a BCC structure. So on the figure you can see a body centered cubic arrangement. Let the edge length be A and the face diagonal, say FD, equal to B. Okay. So if you consider this face, the face diagonal is FD. FD is denoted as B. We have also represented a body diagonal. The body diagonal is represented as AF. So let AF is equal to C. Okay. So we have shown here a body centered cubic lattice with spheres along the diagonal. The edge length is A. The face diagonal represented as FD equal to B and the body diagonal represented as AF equal to C. Now consider the triangle EFD. Okay, so we have considered this triangle EFD. So again, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So in this figure, if we consider FD as the hypotenuse, then the square of FD will be equal to the sum of the squares of the other two sides. So that is FD square is equal to ED square plus EF square. FD is the face diagonal, that is represented as B. So B square is equal to A square plus A square, where A is the edge length. ED and EF here. So EF and ED are the edge lengths. So it is A. So we have B square is equal to A square plus A square. So that is equal to 2A square. Okay. Now consider another triangle AFD in the figure. So, here we can see the triangle AFD. So, similarly, AF square, that is the square of the hypotenuse, AF square is equal to AD square plus FD square, that is the sum of the squares of the other two sides. So, AF is, you can see that it is the body diagonal, and the length of the body diagonal we represent it as C. So, AF square is C square. So, C square is equal to AD square plus FD square. AD, you can see that it is the edge length, it is A. Now, FD is the face diagonal. So, it is represented as B. So, C square is equal to A square plus B square. So, previously we got B square is equal to 2A square. So, substituting the value of B square, we get A square plus 2A square is equal to 3A square. So, if C square is equal to 3A square, then we get C equals root 3A. So, let R be the radius of the sphere. We know that in a BCC structure, on looking onto the figure, there will be 3 spheres touching along the diagonal. Okay. So, you can see here along the diagonal there will be 3 spheres. If R is the radius of one sphere, you can see that the sphere in the middle is touching 2 other spheres. So, here we have from distance A to F, we have R, R, R and R. So, the body diagonal AF is equal to C, so that will be equal to 4R. So, we have 4R is equal to root 3A. So, from this you can calculate the edge length where A equal to 4R by root 3. We know that in a body centered cubic arrangement, each unit cell has effectively 2 spheres. There will be 8 atoms at the corners and 1 at the body center. So, in effect the contribution will be 2. So, the volume of the 2 spheres will be equal to 2 into 4 by 3 pi r cube, where 4 by 3 pi r cube is the volume of one sphere. So, that is equal to 8 by 3 pi r cube. Now, what will be the total volume of the cube? The edge length is A, so the total volume of the cube is A cube. So, that is equal to A is 4R by root 3 the whole cube. So, if you take the cube, you will get 64R cube by 3 root 3. So, we can calculate the packing efficiency. So, how to calculate the packing efficiency? Volume of the 2 spheres, that is 8 by 3 pi r cube divided by the total volume of the cube. So, we have 64 r cube by 3 root 3. So, that will be equal to 68%. So, you have to multiply by 100 also in order to represent it in percentage. So, packing efficiency will correspond to 68% in BCC structure. Now, let us see how to calculate the packing efficiency in a primitive cubic structure or a simple cubic structure. So, here also let the unit cell edge length be A. On the figure, you can see that the particles touch each other along the edge. Okay, so, this is one particle and this is another sphere. They touch along the edge and the edge length is represented as A. So, since there are 2 spheres along one edge, we can represent the edge length A equals 2R, where R is the radius of the sphere. The volume of the cubic unit cell is A cube. So, that is 2R the whole cube is equal to 8R cube. We know that in a simple cubic structure, each unit cell has effectively one sphere. So, the volume of one sphere is equal to 4 by 3 pi r cube. Now, what will be the packing efficiency? So, what will be the packing efficiency? We have seen that the packing efficiency is given by volume of one sphere. We have considered a simple cubic. So, the total number of spheres in unit cell is 1. So, volume of one sphere in unit cell divided by total volume of the cube into 100. So, that will be equal to 4 by 3 pi r cube by 8 r cube into 100. So, that will correspond to 52.4% of packing efficiency. So, we have seen and calculated the packing efficiencies in different types of cubic lattices. We have seen that in a face-centered cubic lattice or a CCP arrangement, the packing efficiency was the highest, corresponding to 74%, whereas in a body-centered arrangement, the packing efficiency was 68%, and in a simple cubic or a primitive cubic arrangement, the packing efficiency was the least, corresponding to 52.4%. In the previous class, we have seen about voids, namely tetrahedral and octahedral voids. So, the number of these two types of voids, that is whether it is tetrahedral or octahedral, depend upon the number of close packed spheres or the number of atoms that touch each other. Let the number of close packed spheres be n. Then the number of octahedral voids generated will also be equal to n, whereas the number of tetrahedral voids generated will be equal to 2n. So, we can see that the number of tetrahedral voids is double the number of octahedral voids in a close packed structure. In ionic solids, the bigger ions will be usually anions, form the close packed structure, and the smaller ions are generally cations. The smaller ions occupy the voids. And if the cation is very small enough, then they generally occupy the tetrahedral voids. And if they are bigger, then octahedral voids are occupied. The fraction of the octahedral or tetrahedral voids that are occupied depend upon the chemical formula of the compound. You should remember that it is not necessary that all the tetrahedral and octahedral voids are occupied, and the fraction of the octahedral or tetrahedral voids that are occupied will depend upon the chemical formula of the compound. So, now let us discuss a few questions based on the occupation of the voids by the atoms and finding out the formula of the compound. So, the first question is, a solid is made of two elements P and Q. Atoms Q are in CCP arrangement, while atoms P occupy all the tetrahedral sites. What is the formula of the compound? So, it is given in the question, we have two atoms P and Q. It is given that the Q atoms occupy the CCP arrangement, or they form a closed packed arrangement, and the P atoms occupy the tetrahedral voids. So, if Q atoms adopt a CCP arrangement, then there are two tetrahedral sites per each Q atom. That is, if the number of Q atoms is n, then there will be 2n tetrahedral voids. So, in the question it is given that all the tetrahedral voids are occupied by the P atoms. Okay. So, if the number of Q atoms is equal to n, the number of tetrahedral voids, so I am representing TD for tetrahedral, tetrahedral voids will be equal to 2n, okay, and the P atoms occupy all the tetrahedral voids. So, what will be the number of P atoms? Number of P atoms will be also equal to 2n. So, that is, for each Q atom there are 2 P atoms. So, what will be the formula of the compound? It will be P to Q. If we take the ratio of P is to Q, so that will be equal to 2n is to n. So, 2 is to 1. So, the formula will be P to Q. So, in a similar way, we can find out the formula of the given compound. Okay. So, now let us see a few more questions. Second question, a compound is formed by two elements X and Y. The atoms of the element Y as anions form a CCP structure, and those of the element X as cations occupy all the octahedral voids. Find the formula of the compound. So, here we have two elements X and Y. The element Y forms the CCP structure. Okay. So, Y forms a CCP structure and element X occupy all the octahedral voids. Okay. So, X occupy the octahedral voids. I am representing OH for octahedral. Okay. So, X occupy the octahedral voids. Now, you have to find out the formula of the compound. Okay. So, the number of octahedral voids in a close packed arrangement will be equal to the number of atoms that form the CCP arrangement. So, here the Y atoms forms the CCP arrangement. So, if the number of Y atoms is equal to n, we can see that the number of octahedral voids will also be equal to n. Okay. Further, it is given in the question that the atom X occupy all the octahedral voids. So, if all the octahedral voids are occupied, then what will be the formula of the compound? It will be XY. And how XY is formed? Number of atoms of Y is n, number of octahedral voids is also n, and if X occupy all the octahedral voids, then the number of X atoms will also be equal to n. So, what will be the ratio of the two atoms? X is to Y is equal to n is to n. So, that is equal to 1 is to 1. So, that corresponds to the formula XY. Now, we will move on to the third question. A compound is formed by two elements A and B. So, atoms of the element B form HCP lattice and those of the element A occupy 2/3 of the tetrahedral voids. What is the formula of the compound formed by the elements A and B? So, here we have two elements A and B. It is given that B atoms form the HCP lattice. Okay. So, B forms the HCP lattice. Let the number of B atoms is equal to N. So, the number of tetrahedral voids in HCP will be equal to twice the number of B atoms. So, 2 into N. We have seen that in a hexagonal close packing, the number of octahedral voids will be equal to the number of close packed spheres, whereas the number of tetrahedral voids will be equal to twice the number of close packed spheres. So, if the number of B atoms is N, the number of tetrahedral voids will be equal to 2N. Okay. So, what will be the number of A atoms? It is given that A atoms occupy 2/3 of the tetrahedral voids. So, that means 2 by 3 into 2n, since 2n is the number of tetrahedral voids. So, that will be equal to 4 by 3n. So, what will be the ratio of A and B? A is to B can be written as 4 by 3n is to n. So, that will give rise to 4 is to 3. So, we can write the formula of the compound as A4B3. Okay. So, in this manner, we can find out the formula of the compound given the number of voids or the arrangement adopted, whether it is a cubic close packing or whether it is a body centered, etc., adopted by the spheres. Now, let us move on to a few assignment questions. First question, the percentage of free space in a body centered cubic unit cell is given by option A 30%, option B 32%, option C 34% and option D 28%. Question number 2, the most efficient packing is present in option A HCP and BCC. HCP is hexagonal close packing, BCC means body centered cubic packing. Option B HCP and CCP. CCP is again cubic close packing. Option C BCC and CCP. Option D BCC and simple cubic cell. So, among these options you have to find out the most efficient packing present. Question number 3, the packing efficiency of the face centered cubic unit cell is, assuming that the atoms are touching each other. Option A 68.04%, option B 52.4%, option C 74% and option D 79.06%. Fourth question, in naturally occurring corundum, the oxide ions form the hexagonal close packing and aluminum ions occupy 2/3 of the octahedral voids. So, what is the formula of corundum? Fifth question, a compound is formed by two elements X and Y. Atoms of the element Y as anions make CCP, that is cubic close packing, and those of the element X as cations occupy all the octahedral voids and half of the tetrahedral voids. So, what is the formula of the compound? So, try to find the answers for these assignment questions and we will discuss the answers in the next class. So, today we have seen the calculation of packing efficiency in various close packed structures, namely face centered, body centered and simple cubic structures. We have also discussed a few questions based on the number of voids and the formula of the ionic compound. We will discuss the answers in the next class for these assignment questions, and we will see a new topic related to solid state. Thank you.